Okay, so dot product of vectors. Dot product of vectors is a lot like multiplication. It's kind of the next step after adding and subtracting. But because it's vectors, it's not really just multiplication. So we're going to learn about dot product today, and we're going to find out it's a very easy process. We're going to identify the angle between vectors with a little formula. That'll help us out with that. And in fact, we're not even going to do the work. And I think we got to this last year and said, gosh, this is a little bit over the top from the other stuff we're doing, and you did have it in 9th grade science. So we thought, yeah, we've got to put something in. This probably isn't the most important thing in the world. So we are just going to be doing those first two of the objective. So vectors can be multiplied in two different ways. One we already talked about, scalars. You know, if you need to change the magnitude, you change it by multiplying by a scalar of some type. So both of which are derived from their usefulness for solving problems in vector applications. Cross product, or vector product, also called outer product, but there aren't enough names for that, results in a vector perpendicular to the plane of the two vectors that are being multiplied. Yeah, they're making that sound much harder than it is. So, and actually we don't cover cross product in this class. We're just going to cover dot product. So it is a little tougher than dot product, but we're not going to do that. So that takes us into a third dimension and outside the scope of this chapter. So we're not doing cross product. What we're going to do is dot product, which is fitting in line with what we've done for the scalar product. It's also called an inner product. You'll kind of see why when we're going through this. So it results in a scalar. In other words, the dot product of two vectors is not a vector, but a real number. It's a scalar. That's what we get when we're trying to find the dot product. It is the important information conveyed by that number that makes the dot product so worthwhile. So it has connections to what we've been doing already without going into a third dimension and making this really difficult compared to what we've been doing. Now, we talked about this earlier, that an arrow doesn't really mean a vector. It means it's representing a vector. So our bold little u, we learned right off the bat, it really should just have one arrow up there. And the arrow isn't the vector. It's showing direction and it's showing magnitude, but it's just a representation. That's all it is. So we use those notations as the vector u represented by vector pq. Other notations used, we've come across these, love the component form, the math, very super easy with the component form. And the first thing we do when we see this vector form, ai plus bj over here, is we change it into component form, because component form is so much easier to use for the math. But they're interchangeable. We don't want to forget that, so that when we see the homework and they have it in that vector form, we can change it back to component form. Now, dot product. How do you find it? Well, we have a vector with I and j components and another vector with I and j components. And we see that what they're really doing is they're saying, well, take u1 times v1 plus u2 times v2. What does that mean? Well, that means if we take these two and write them in component form, we're supposed to take the x component times the x component, get an answer. The y component times the y component, and get an answer. And then add those two results together. So for us, it'll just seem like x times x plus y times y, dot product. Done. That's all we have to do. So vectors are used extensively in mathematics and science applications, such as determining the net effect of several forces. We've already had the force of a ship and then the force of a stream coming back added, the airplanes with wind, all of that good stuff. Oh, I'm recording, Lauren. Oh, thank God. Ooh. That says several forces. We're not doing several. So far, we've just done two at one time. That's probably enough for a little introduction to vectors. If you really enjoy working with vectors, there is always a course course called Vectors and Matrices whenever you go to college. It just focuses on working with vectors and strictly vectors and matrices. That's it. So we want to do this part where we're computing the work done by a force acting on an object in science class. We're not going to do that. And we are right here where we have the formula for the dot product. And you can see it is the x times the x right here plus the y times the y right here. That's what you do. But it turns out there are many properties that we think of with normal multiplication and addition that also work with the dot products. It says here, u times v equals v times u. That's important. That's the commutative property. And that doesn't always work. When we were working with matrices, you couldn't do that. Matrix A times matrix B was not necessarily the same as matrix B times matrix A. So it's good to know that the commutative property works there. Number 2 is interesting because it says you could really do the dot product to find the magnitude. Because if I think about it, this little squared here, if I took the square root of the dot product of u times u, that would give me the magnitude. Well, I already know I'm finding the magnitude, but if the magnitude formula eluded me while I was taking a test, I could just use the dot product and take the square root. That'll work. This little bugger, you're multiplying 0 by any vector. Of course, it's a scalar. You're going to get 0 when you get done. Here we can distribute our vectors for dot products. That doesn't matter if we distribute from the right or the left. It works both ways. And this one says you can also use the associative property. You can change around the parentheses and you'll still get the same answer. It's good to know because what it does is it tells us a lot of the properties that hold for normal multiplication also hold for dot products of vectors, which is pretty good. So now, look at that little word, proof. Let U be component form, u sub 1, u sub 2, and b sub 1, b sub 2. Proof property 1. Okay, property 1 starts off like this, u times b. All right, so what I know so far is that what we're supposed to do is take u sub 1 times b sub 1 plus u sub 2 times b sub 2. Okay, and what I want to do is get them to turn around. That's what I need to do, but I can only use properties that I knew before, in fact, before we took this class that we knew. And that's this. Is 2 times 3 the same thing as 3 times 2? So we can turn those around. And we can do the same thing for the back one. And why was that important? Because we want to change the order. I mean, we had u's first when it was u times b, and if we want to prove b times u, we just needed to get the b's up front, which we just did. So b times u, there it is. Little teeny step, where we say, hey, that's just multiplication, and I know how multiplication works, so I can use that commutative property. Property 2, well, that takes a little more finagling. Property 2 says we're supposed to start with u times u and figure out how that gets us the magnitude of u squared. All right, well, let's see. That would be u sub 1, u sub 2, u sub 1, u sub 2. Okay, so if we did the dot product, that would give us u sub 1 squared plus u sub 2 squared. I'll have to figure out how to make that to the magnitude squared. So now I'm going to work backwards. Magnitude of u squared. So I think, well, what does that equal? That equals the square root of u sub 1 squared plus u sub 2 squared. But then they have that power of 2 up there. Squared. Well, isn't that what this is? Aren't square roots and squaring inverses of each other? So this is really a kind of two-step proof where we just say, hey, this is what we would normally get. And this is what the magnitude is, so it leads me to this. And there it is. So 2 steps. It's kind of one of those things where you wonder, am I overthinking this? And usually we are, because these vectors just follow a lot of the same rules as multiplication does. So now enough of that proving garbage. Let's find it out. We have component forms here with numbers. Here's what we know we're supposed to do. X times X plus Y times Y. Oh, that doesn't look too complicated. There it is. There's that one. The real number, what's the scalar? It's 23. It's 3 plus 1 times -4 plus -2 times 3. -4 and -6. Good. Got product. Uh-oh. C looks like a challenging problem. What would you do first? What did component form exactly? 2, -1, 3, -5. Now it's hardly a challenge. 2 times 3 plus -1 times -5. So we've got 6 plus 5. I'm liking that product. This is not bad. We just needed to know how to do it. Once they told us how to do it, hey, this isn't bad at all. So down here at the bottom, little thingy that says property 2 of the dot product gives us another way to find the length of a vector as illustrated in example 2. That's because now we wouldn't necessarily need to know how to find magnitude. We do anyway. We did a bunch of assignments on it. We know it's the square root of a squared plus b squared when we're dealing with a vector in component form. But this is saying you could also figure out what the magnitude is by using the dot product and then just taking the square root. Because get that. So let's give it a try. Use the dot product to find the length. Well, first of all, I would want to know that I'm doing it right. So I'm going to do this first. I'm just going to go back to finding magnitude because it's not hard. We take the a and square it and the b and square it. So we'd say, well, that's 16 plus 9. It's 5. Square root of a squared plus b squared. So that's what we should come out with when we get done with this. So let's see if we do. Well, if we do the dot product of 4 negative 3, we're going to get 16 plus 9, which is 25. Then I remember that's the magnitude of u squared. So I'd have to take the square root of both sides. And that would give me 5. Now, how do I know it's not negative 5? I mean, whenever we do square root stuff, aren't we supposed to do plus or minus 5? No, this is a speed, it's a length, it's a distance. All those things that we're going to talk about will use positive values. So we definitely could use dot product. We just have to remember to take the square root when we get done. That's the big piece. So now, this was the other thing we had to learn today. Our other objective dealt with finding the angle between the vectors. So let u and v be 2 non-zero vectors in standard position as shown. Okay? Here's u, here's v, there's theta. It may look 90 degrees, but we don't know what it is. We need to be able to find it. What is that angle between those two vectors? So the angle between u and v is the angle theta, where theta is going to be between 0 and pi, or 0 and 180. And here's where it gets weird. In this section, the book tends to give degree answers, which we should absolutely stick with just for chapter 6, is the degrees. But when they do them as review problems towards the end of the chapter, they put everything in radians. So what I want to make sure is, does everybody remember how to take degrees and change it into radians? Right, multiply by pi over 180. People were lip syncing that. That's what you do. So if you want to check it in the back and you see that your answers are in the back are all radians. Multiply by pi over 180, you'll see things are good. So the angle between any two non-zero vectors is the corresponding angle between their respective standard position representatives. Again, they're making it sound harder than it is. We're just trying to figure out what is that angle between these two vectors. And we get a couple of nice little formulas here. The first one says, well, you're just going to take the dot product of u and v, and you're going to divide it by the product of the magnitude of u times the magnitude of v. That's what you're going to do. And that's driving me bonkers right now. There's way too many people to look at that and think, oh, absolute value. No, it's not absolute value, it's magnitude. Magnitude. So if that's how we get the cosine of the angle, and we need the angle, we're just going to do an inverse cosine function. Get it back. That's what we have to do so we can see it. Now there's a proof of this, and it's a good review because it comes from the law of cosine. So I'm just going to walk you through it here and how it works. We apply the law of cosines to the triangle determined by u sub uv, the two vectors uv, and v minus u in the figure that we had above. And so take a look at this and see v minus u, that quantity squared, equals magnitude of u squared plus magnitude of v squared minus 2 magnitude of u, magnitude of v, cosine theta. All right, so where to go from there? We know that v minus u squared is going to be v minus u times v minus u. That's what it is. So we expand that in order to see, are some things, good things going to happen here? Is there going to be something that drops out to add or subtract? What's going to go on over on the left-hand side? So we would get v squared minus uv minus uv, so 2 of those, plus u squared. So we write that as the magnitude of v squared minus 2 uv plus the magnitude of u squared. Now hopefully you see, hey, that's a good thing, because we could subtract the magnitude of v squared and the magnitude of u squared from both sides. Just thinking right now about troubleshooting here. If somebody's thinking, why does it have that magnitude stuff on there? Because we're always talking distance. Remember, this is still a triangle, so we're talking distance. So if we subtract the magnitude of u squared and the magnitude of v squared, then this is gone, and we're going to get this. And this is the only piece we have left over here. Minus 2 u times v equals negative 2 magnitude of u magnitude of v cosine theta. And now we want the angle. So we would solve that for cosine theta, which means we would divide. And the negative 2's would drop out. So the dot product of u and v over the magnitude of u times the magnitude of v. And then we just use inverse cosine. And add. These extra little lines on there. So dot product on top, magnitude of each on the bottom, and see what you get. That's what we have to do. Inverse cosine action. Oh, all right. So use an algebraic method to find the angle between the vectors u and v. Use a calculator to approximate exact answers when appropriate. So we want the math to be perfect all the way to that, like normal. And then if we have to round, we have to round. So I remember my little formula said I'm supposed to find u dot v over magnitude of u, magnitude of v. Now the reason I write that down first is because what I want to do is think through the pieces that I have to use this formula. I have to find the dot product. Okay, so dot product. 2 times negative 2 plus 3 times 5. Negative 4 plus 15. Little 11 right there. And then I remember it's pretty easy to find the magnitude when it's a component form. All you have to do is the square root of a squared plus b squared. We just learned you could also do dot product and take the square root and that kind of stuff too. But we've already learned the other part, so why not make use of it? This would be 4 and 9. So a squared plus b squared would be 13. Square root of 13. Remember, just in case anybody's forgot, find magnitude in component form. Square root of a squared plus b squared. So what would we get for b? Magnitude of b. Square root of 29. Yeah, neither one of those is very pleasant, is it? Well, we can multiply those together because they're both square roots. So we get the square root of whatever 13 times 29 is. And that's 377. And remember, that's the cosine of theta. So if we want the angle, we're going to do inverse cosine. And now everything's been perfect up to this point. So now if we get a decimal, we get a decimal. That's just how it works. So 11 divided by the square root of 377. That's 277. Oops, thank you. More information. I mean the calculator not getting along. Second inverse cosine. There we go. 55.491 degrees. Now, as usual, drawings are not to scale, but you should always ask yourself, reasonable that would be 55.491 degrees? Yeah, reasonable. You know, if we drew those vectors out, that's exactly how we would draw them, and it makes sense. It should be about 55.491 degrees. Alrighty. This one. 2, 1, negative 1, negative 3. Find me the dot product, please. -5, -6. I thought I heard both of them. Which is it? -5. We've got -2 plus -3. So -5 over. Please find me the magnitude of square root of 5. Now finding the magnitude of 8. Well, that's kind of nice. Let's see what that comes out to be then. We've got -5 over the square root of 50. Wait a minute. Square root of 50. 25 goes in there twice. Well, the 5s will cancel. Wait a minute. I think we know this one without using the calculator. Because if we rationalize the denominator, wouldn't this be negative square root of 2 over 2? What angle, and I'm just saying generically, square root of 2 over 2. What angle does that work for? 45. Okay. So it can't be over here. Could be over here. So from here to here. What would those degrees be? 90 plus 45, what would you get? 135 degrees. Now, what do you suppose you would get if you did use a calculator? 135 degrees, exactly. But as we're reviewing for the final, I'm hoping that we haven't lost all of the trick, that there are still a few pieces that we're hanging on to as we go through here. And yeah, definitely 135 reasonable for what we see there. All right, last topic is not really doing any new math. It's just understanding the results of what we get, and that is this fancy word, orthogonal, that we're going to see on the next page. In geometry, hopefully somebody was breaking apart words for you. Ortho means to make straight. That's why when you see an orthopedist, they're trying to make things straight. Now that's just their job. That's what they do. So if vectors u and v are perpendicular, that is, if the angle between them is 90 degrees, well, then we should have the magnitude of u times the magnitude of v times the cosine of 90 degrees. Now take cosine of 90 degrees. 0, 1. Hey, that's 0. It should be 0. So if they're perpendicular, we should get 0. The cosine of 90 is 0, and that's what it is. So how do we know if the vectors are orthogonal? If their dot product is 0. That's going to work. So the terms perpendicular and orthogonal almost mean the same thing. Not completely and totally. And that's because of the 0 vector. The 0 vector kind of messes things up. This works for everything else, but the 0 vector doesn't have a direction angle. So technically speaking, the 0 vector is not perpendicular to any vector. So it's one of those things where we have kind of this little disclaimer. Yes, they are orthogonal if u times v equals 0. Unless one is the 0 vector. That's the little piece right there. So, however, the 0 vector is orthogonal to every vector. That kind of clears it up. We'll just say, hey, the 0 vector is orthogonal to everything. Except in the special case, orthogonal and perpendicular are going to be the same. So if we get a dot product of 0, we know we could say the vectors are orthogonal. Yeah. So note, two vectors are parallel if one is a scalar multiple of the other. I think I talked to you about that in 6.1. We were going through that as well. If it's just a scalar multiple, then it's called parallel. So down here, prove that the vectors are orthogonal. All we have to do is show that their dot product is 0. Now we might want to show a little work. I mean, the other ones we were kind of doing in our head. So we might want to actually write down 2 times negative 6 plus 3 times 4 equals negative 12 plus 12, which equals 0. But there it is. The resultant vector of 0 shows that they are orthogonal. They are orthogonal. There it is. Oh, that grammar went all over. So that's all we have to do if we want to show they're orthogonal. Now, obviously, you start throwing some variables in here, and things can get a little more difficult, but not a lot, just a little bit. So this says exploration. We have angles inscribed in semicircles. So here's our angle. Inscribed means it's fitting right inside of there. And it says angle ABC is inscribed in the upper half of the circle. And in geometry, which was, I know, eons ago, what you learned was that whatever you have for this cutoff arc, this inscribed arc angle will be half of that. So this is 180 degrees, and this little bugger back here is 90. Well, if it's 90, then this is a right triangle. And these sides squared, added together, is supposed to equal that side squared. So this says that. X squared plus y squared should equal a squared. Now it says for a equals 2, figure out the component forms of the vectors u, which is vector VA, and v, which is vector VC. So up here, we're supposed to make this a negative 2, 0, and this one a 2, 0, and go through and see what happens. So, finding the component form. All right, we can do that. We've done that before. All we have to do is terminal minus initial. That's all we have to do. So u is from B to A, but A is the terminal point here. So we'd have x minus a negative A. Oh, A is the terminal. I had to turn around backwards. They're going this way. There, I put an arrow on there. That'll help. Negative A minus x. And 0 minus y is negative y. And then the other one is BC, so that one will be a minus x, and 0 minus y. Now, if that's a 90-degree angle in there, when we do the dot product for this, we're supposed to get 0. So number 2 says, find the dot product. Let's see what happens. All right, so the dot product for this would be negative a minus x times a minus x plus negative y times negative y. Well, that's some nasty FOIL, but it is FOIL. So negative a squared plus ax minus ax. Hey, cool, that's gonna cancel out. Last times last plus x squared plus, well, this is gonna be y squared. How's that supposed to come out to 0? Because x squared plus y squared is the same thing as a squared. So if we substitute that in here, this is going to say negative a squared plus a squared, which of course is 0. So we use the information that they gave us up above and say, well, let's use that then. We can show, hey, that's negative a squared and a squared. It's going to work. Now, that was actually part 3. And I did that because the generic one, I think, is more worthwhile to you than using the negative 2, 0 and the 2, 0. You could, and we will, but this one works for any numbers. So when we do the negative 2, 0 and the 2, 0, you're going to see it's kind of silly to go through that. So, in fact, maybe I won't even do that. Maybe I'll just give you work time instead. Yeah. Does everybody see this is going to work no matter what numbers we put in there? Whether or not they use their negative 2, 0, their 2, 0? Yeah. So I think I'll just skip putting the 2 in there instead. So objective today was dot product. That was a big piece of it, and finding the angle in between. 43210 means dot product and finding the angle in between. But you know what? I'm going to do them separate. I want to see which, if anything's giving you trouble. So dot product. 43210, just dot product. So most people feel really good about dot product. All right, angle between the two vectors. So I'm just going to take a little getting used to with that formula. Huh? All right. Well, let me get this up here. There it is. I remember this going really, really fast because that product is not tough. And there are a few of the finding the angle in between. That was the last new stuff you're going to learn this year. Everything from here on out is review.